So today we're going to do operations with radicals. We graphed them, we simplified them. Now we're going to do operations. Our next class and last class is solving. So graph, simplify, operations, solve. That's our 4 lessons that are taking forever because of snow days and stuff. But so starting off, it says the index, and we talked about this before, but the index is the type of root that you are taking. So for example, a cube root, what's the index? A 7th root, what's the index? 7. Yeah, the other word is called the radicand, with like an A and D at the end, radicand. That is the number or variable under the checkmarky looking sign. So that in this case, the radicand is 17. What's the radicand of this one? 8. Yeah, what's the index of this? 2. Yeah, square root's a 2 root. We just don't write the 2, okay? So in example 1, we're just practicing that. What is the index? I'll put an I. 7. What is the radicand? I'll put an R. 512. So this will be on your snapshot today. You just have to identify what is the index and what is the radicand. Okay, now example 2 isn't a radical yet, but we practiced that last class numerous times. We did dominoes with it and all that stuff. So how could I convert this into a radical? The cube root, good, of x to the 4th.
I have a question.
Yeah.
So is the radicand everything that's under this?
Yep. So what is the index in this case?
3.
The index is 3.
So what is the k considered?
And the radicand is what in this case? X to the 4th. What are you talking about, K?
Yeah, so what if there's something not the back of the root?
Oh, this isn't an equation. This is just an expression.
Okay.
So if there was if this was an equation, like a plus 4 at back,
Yeah.
that's still, we're only talking about the radical stuff.
Okay.
So it'd still be the same answer. All right, moving on. So now we're going to kind of start our operations. So adding and subtracting and multiplying. It's pretty easy. So what I have kind of set up here is kind of an A and a B. So it says, what do the following problems have in common? So let's take a look at A. X plus X. What would our answer be?
2x.
2x, right? Because we have 2 of them. We've known that for many years. X plus X means we have 2 X's, okay? Now, how does that compare to B? It's basically the same thing, right? It's just we're saying that X is the square root of 5. So what is, based on kind of that pattern, what is the square root of 5 plus the square root of 5 going to be? 2 square roots of 5. So just like the x's above, I have something plus the exact same thing that is 2 of that thing. So really, we're just combining like terms here. I'll put combine LT, combine like terms. Okay, so now look at the second section there, the second A. A plus Y. Or sorry, X plus Y. Can we combine those together? No. So what's our answer?
X plus y. X plus y.
There's X plus Y, that's it. If you can't combine them together, they just stay separate. Those are not like terms. So X plus Y is just X plus Y. So on B, underneath it, what is the square root of 5 plus the square root of 7?
Square root of 5 plus 3.
So that's it. If they're not the same radicand, I'm going to use that vocabulary we just learned. So these are called the radicands. If they're not the same radicand, then they're not like terms and they cannot combine. So that takes us to kind of the last section there. We have, up above, I have 2x plus 3y plus 4x. So what could we combine there? Good, we'd have 6x's plus 3y's. So we had a couple like terms, but the y's still cannot combine. So how do you think that applies to down here? These ones, the first one and the last one, just like above, have the same radicand. So how many square roots of 5 do I have? 6 square roots of 5 plus 3 square roots of 7, and that's all there is to it. So like what we basically just figured out, when adding or subtracting radical expressions, first simplify the radicals. Once simplified, combine like radicals, okay? So what I mean by simplify, 3, 3, and 7. Can those simplify any further? No, they're all prime numbers. So what can we combine?
3.
The cube roots of 3. So how many cube roots of 3 do I have?
6.
Good. 4 plus 2 is 6 cube roots of 3. That one's totally different. It's not even a cube root. So it has to be the same type of root as well. So that's just minus the square root of 7, and that's all there is to combine. I should say the index also has to be the same. So you can't add a cube root to a square root. Okay, now example 4. What's different about example 4 than what we've kind of done so far? So what do you notice about this number and this number? They're prime. What about 5 and 7?
Prime.
They're prime. Everything we've done so far was prime. 3 and 7 are prime. 5 is prime, but 45 is not. So that's what I'm saying up top. You have to simplify first. So at first, does it look like any of these are the same? No. Obviously, the 5, the 45, and the 125 are not the same. But if we simplify them, they might be. This might be hiding in there. Okay. So let's do our 45. Let's just do a factor tree. Some of you are maybe kind of getting good at this. What's a perfect square that 45 divides by? 5 and 9. Good. And 9 is obviously 3 and 3. So what comes out front? 3 square root of 5. So now, can you see that we actually will be able to combine those? Okay. Do the 125 on your own. Practice simplifying 125. Should just take a couple seconds. Okay, how does 125 simplify?
5.
Yeah, so 125 is 25 times 5, which is 5 and 5. So 5 with a 5 left over. So plus, because a plus sign, 5 square root of 5. So they can actually all simplify. They're all, when you simplify them down, they're all the same radicand, right? They're all square roots of 5. So what's 5? 5 of something minus 3 of something. 2 plus 5. 5 square root. Oh, sorry. Wrote it backwards. 7. 7 square root of 5 is your answer. Bless you. So if they don't look like they're the same, first make sure they're simplified, and then go about doing your business. Okay, trying now, based on that, you should be able to do kind of example 5. They're fourth roots, but you should still be able to simplify them. Obviously, this one is prime. So 2 fourth root of 2, there's nothing we can do about that. But go ahead and practice simplifying 3 fourth root of 162 real quick. So that becomes minus 9 fourth root of 2. So can we combine these now?
Yes.
Yes, they're both fourth roots of 2. The indexes match, the radicands match. What's 2 minus 9? Negative 7 fourth root of 2 is your answer. So, when multiplying radical expressions, you multiply the radicand of like index radicals. Excuse me. So I'm going to get a little bit more basic first. So let's say I have the square root of 2 times the square root of 3. We only care about like terms if we're adding and subtracting. If we're multiplying, you can still multiply them together. So just like 2 times 3 is 6, the square root of 2 times the square root of 3 is the square root of 6. So you actually multiply the radicands together. Does that make sense? So you might write that up to the top just so you have an easy example. So what is, just to practice a few of these, what's the square root of 3 times the square root of 3? It's the square root of 9, which is 3. That's a perfect square, right? So earlier this year, we did some of those when we rationalized the denominator. Remember, when you multiply a square root times itself, basically what that is the square root squared, right? Something times itself is squared. And a square root and a square undo each other. They cancel each other out. So that's why we get that 3 down here. Okay. So whichever way makes sense for you to think about, that works. So just to practice that, what's the square root of 4 times the square root of 4?
Square root of 16.
Which is 4. What's the square root of 30 times the square root of 30? 30. What's the square root of 400 times the square root of 400? 400. What's the square root of 7 times the square root of 7? 7. That's all there is to it. Okay. Now one more. Let's say that there's a number in front. So let's say I have 2 square root of 3 times 3 square root of 2. So we're going to multiply the numbers in front. The whole numbers get multiplied together, and the radicans get multiplied together. So kind of if we had 2x times 3y, what would our answer be? 6xy. Okay. So in this case, we multiply the. Oops. Oh, don't want that. So we multiply the 2 times the 3 in front, that gives us 6. And then we multiply the radicans, so that gives us 6. So our answer there would be 6 squared root of 6. Okay, so now let's just kind of apply those to a couple examples here. So we need to distribute here, so let's do example 8. We need to multiply that through. So what is the cube root of 3 times 2 going to be?
2 cube root of 3.
Yeah, kind of like x times 2. We typically write as 2x. So let's write the whole number in front. So 2 cube root of 3. And then we have to distribute the cube root to the other one. So plus the cube root of, and then we multiply the radicans underneath. So we multiply 3 times 9 is what? 27. Yeah, now you have to ask yourself, can that simplify or is it a perfect cube? And it is. What's the cube root of 27?
3.
It's 3. So this is really 2 cube root of 3 plus 3. That's all for that one. So it's kind of like 2x plus 3. We still have to keep them separate because one's multiplied times the cube root of 3 and one's not. Now you could I write this backwards? Could I write it as 3 plus 2 cube root of 3?
Yes.
Yeah, you can switch the order of adding. It's still the same thing. Okay, give number 9 a shot. So we do need to, I'll give you a little hint. You got to FOIL that out. So first, outer, inner, last. See if you can apply those properties of multiplying and simplifying to get to an answer. Most of you kind of got through the first step. So what's the square root of 2 times the square root of 2? It's the square root of 4, which we know will end up being 2, but I'll keep it as that for now. And then we multiply the outers. So square root of 2 times the negative square root of 8 is just negative square root of, multiply the numbers underneath, we get 16. And then we do the middle 2. So the square root of 3 times the square root of 2 is square root of 6. And then the last 2, the square root of 3 times negative square root of 8 is negative square root of 24. Good. Now, that very, very rarely after one step is that going to be your answer. Like 99.89% of the time, you're going to have to simplify something. So there are 3 things we can simplify here. What's the square root of 4? 2. Minus, what's the square root of 16? 4. Well, that's nice. Plus, now 6 is 6 is 2 and 3, so that's not going to simplify. There's not enough to come out, so that just stays the square root of 6. But the 24, we can do a little factor tree, would be 8 and 3, 4 and 2, 2 and 2. So minus in front, that's just the sign. What comes out? 2 square root of There's a 2 and a 3 that didn't have a pair, so 6. So now what do you notice?
You can buy.
Well, yeah, obviously we can do 2 minus 4 in front, so what's 2 minus 4? Negative 2. And then both of these came out to be like terms. They're both square roots of 6. So what's 1 square root of 6 minus 2 square root of 6? Negative 1 square root of 6. And you don't have to write the 1, but... And that's it, because that's an integer, that's a radical, they stay separate. They're not like terms. So, a few steps, yes. Hard, no, not necessarily. Okay, last one for today. We're not going to do number 8 and 9 at the bottom. You can scratch those out, but I do want you to write 9b in and give that a try real quick. So, what is 2 times 2?
4.
4. Now, if we do the outer ones, we'd have 2 times the square root of 3, which is just 2 times the square root of 3. One's a whole number, one's a radical, so they just stay separate. Plus, what do we have in the middle? It's the same thing. It's 2 square root of 3. And then a positive times a negative is a negative. What's the square root of 3 times the square root of 3? Square root of 9, which is a perfect square. The square root of 9 is 3. So this is why they're called conjugates, because the middle two, negative 2 square root of 3 plus 2 square root of 3, cancel out. And what's 4 minus 3? 1. Uno. That's your answer. So if you remember, just factoring, let's say if we had x plus 2, x minus 2, how would this FOIL out? So x times x is x squared. Minus 2x plus 2x, we know are going to cancel. And then what is 2 times negative 2? Negative 4. So that's why the middle two cancel out, and we're left with x squared minus 4. So going backwards we call factoring. So do you remember factoring differences of squares?
Yeah.
We break it apart. One's positive, one's minus. What times what is x squared? And what times what is 4? 2. So x plus 2, x minus 2. So that's how we use the conjugates last semester.